Okay, exam 4 review. Question 1. First we need to rewrite the integrand to make it easier to take the integral. So this can be written, you notice that the denominator is a single term, but the numerator is multiple terms, so you can rewrite this as separate fractions. X over the square root of x minus 2 over the square root of x. And that simplifies. X divided by the square root of x is the square root of x minus 2. Now, the square root of x down here could be thought of as x to the 1/2. And if we want to move it back up to the numerator, we can give it an exponent of x to the negative 1/2. Matter of fact, it's when you give this term here, I'm going to make that have an exponent of positive 1/2. Okay. Now we can take the integral. We can take separate integrals now since we have two separate terms. This can be the integral of x to the 1/2 dx minus 2 times the integral of x to the negative 1/2 dx. Okay, and then taking each integral separately, x to the 1/2, integral of x to the 1/2, you increase the power by 1, it becomes 3/2, then you divide by 3/2. So this is x to the 3/2, and then instead of dividing by 3/2 like this, dividing by 3/2 is the same as multiplying by 2/3. Okay, and then minus 2. And if we add 1 to negative 1/2, that's positive 1/2, and then we could divide by 1/2, but rather than dividing by 1/2, that's the same as timesing by 2, and we have the constant of integration. So final answer is 2/3 times x to the 3/2 minus 4 times x to the 1/2 plus c. Okay, question 2. We're actually a little bit more simple of a problem. Just take the separate integral of each term, so it's going to be negative 2 times the integral of x squared plus 7 times the integral of x, and then the integral. So now we have negative 2, then we increase the exponent by 1 and then divide by that. And then here we make same type of thing, increase the exponent by 1, divide by that. And then integral of dx is just x. Then we have the constant of integration. Question 3. We need to find the cost function. Now we've been given the marginal cost. The marginal cost is the derivative. You notice here it's a dc over dx. So if we took the integral of dc dx, that's just going to result in that term canceling, so we're going to end up with a cost function. So what we need to do is take the integral of 1/70th x plus 60, okay, that's equal to 1 over 140 x squared plus 60x plus c. This is the cost. Now, this is a cost function that could be different depending on the value of c, but they've given us an initial condition here. It's got a fixed cost of $3,000 when x is 0. So in order to find this constant of integration, we can set the cost to 3,000, and then all the x's can be set equal to 0, and that's going to allow us to solve for c. Now, 60 times 0 is 0, 0 squared times 1 over 140, that's 0. So 3,000 is equal to c. So the cost function, the particular cost function here, is 1 over 140 x squared plus 60x plus 3,000. Okay, question 4, taking the indefinite integral, we're going to have to use u substitution here. So if we let u equal 2 plus x to the fifth, and du is equal to 5 x to the fourth dx. So we have the x to the fourth and the dx, but we're missing this 5. So what we need to do is multiply the integrand by 5, and then to balance it back out, we can multiply the outside by 1/5. So now we have this 5x to the fourth dx right here, so we can replace that with du. This term can be replaced with u right here. So this turns into 1/5 times the integral of u to the 1/2 du. And so this equals 1/5 times 2/3 u to the 3/2 plus c. Now this 2/3 here, we're multiplying by 2/3. Kind of skipped a step. We increase here the exponent by 1, then divide it by 3/2, but instead of dividing by 3/2, that's the same as timesing by 2/3. Now we undo the substitution, and we're going to get 2 over 15, and then u is equal to 2 plus x to the fifth to the 3/2 plus c. Okay, another u substitution. We can let u equal 1 plus 2z, so du is equal to 2 dz. Now we have the dz that we need, but we don't have a 2. So what we need to do is multiply a 2 inside. But in order to balance things out, we'd have to multiply here by 1/2. Now we have the 2 dz that we need right here, 2 dz. And so we're going to let that substitute to be du, and then inside here, actually I'm forgetting something here, it's to the 6th power, there we go. And then this is substituted with that, so our integral becomes 1/2 times the integral of u to the 6th du. So we're going to get 1/2 times u to the 7th over 7 plus c. Now when substituting here, we're going to get a denominator of 14. In the numerator, we're going to have 1 plus 2z. Just a little lower. Denominator of 14. In the numerator, if we unsubstitute for u, we're going to get 1 plus 2z to the 7th power plus c. Okay, question 6. This time u is going to equal 7x plus 9. Du is equal to 7 dx. So we have the dx here, but we don't have the 7. So this turns into the integral of 7 times 7x plus 9 to the 1/4 dx. But since we multiplied here by 7, we got to multiply by 1/7. Now we can make the substitutions. This is going to be u 1/4 du. This turns into 1/7 times 4/5 u to the 5/4. Okay, now I'm substituting here. We're going to get 4/35 and then 7x plus 9 plus c. C is raised to the 5/4 plus c. Okay. Question 7, still on this u substitution, so u can equal s squared plus 2 du then is 2s ds. I actually have everything we need. We have the 2s and the ds. So this becomes the integral 1 over u to the 5th times du. And we can change that into the integral of u to the negative 5th power times du. That changes into u to the negative 4 over negative 4 plus c. Final answer is 1 over negative 4 times s squared plus 2 to the positive 4th power plus c. Question 8. We're going to let u equal negative 2y du then. It's equals to negative 2 dy. So we have a dy, but we don't have that negative 2, so we need to change the integrand into negative 2 times e to negative 2y dy, and then multiply it by negative 1/2 in front. So now the integral turns into negative 1/2 times the integral of e to the u du, which is negative 1/2 times e to the u plus c, which turns into negative 1/2 times e to negative 2y plus c. Okay, question 9, we're going to let u equal 6x to the 4th, so du is equal to 24 x to the 3rd dx. So we have the x to the 3rd dx here and here. We're missing the 24, so this becomes the integral 24x to the 3rd times e to the 6x to the 4th dx. But since we multiplied by 24, we multiplied by 1/24. So now we can make the substitution. This turns into 1/24 times the integral of e to the u du, which is 1/24 times e to the u plus c, which is 1/24 times e to the 6x to the 4th plus c. Okay, question 10. If we let u equal 5x to the 3rd plus 7, then du is 15x squared dx. Okay, so we're going to have to change the integral here a little bit. This is going to be integral of 15x squared over 5x to the 3rd plus 7 dx, and we have to multiply it by 1/15 up front. Okay, so this turns into 1/15 times integral of 1 over u du. Now the integral of 1 over u du, or simply the integral of du over u, is equal to the natural log of u. So this turns into 1/15 times the natural log of u plus c, which turns into 1/15 times the natural log of 5x to the 3rd plus 7 plus c. Okay, starting at number 11, we get into definite integrals, and we first need to find the antiderivative or the integral of this inside. So this is going to be x squared over 2, which is going to cancel with that negative 2. Then we just, this integral of 6 is equal to 6x. So this is equal to negative x squared plus 6x. This is the antiderivative of this. Okay? Now we evaluate the antiderivative from 2 to 4. So that is going to be negative 16 plus 24. That's the antiderivative evaluated at 4. Now we're going to subtract the antiderivative evaluated at 2. So that's negative 4 plus 12. This turns into 8 minus 8, which is 0. Now, what's happening here, the definite integral does represent an area under a curve. How can the area be 0? Well, if we were to graph this curve right here, negative 2x plus 6, actually a line, so we go up to 6. The slope is down 2 over 1, then down 2 over 1, then down 2 over 1. So the line looks something like this. Now, if you wanted to find the area between 2 and 4, here's where x equals 2, here's where x equals 4. So it's actually an area above and below the x-axis, and since it's below the x-axis, it's considered to have negative area. This above the x-axis has positive area. Both areas would be equal to each other, but opposite signs. So when you add these two together, it would result in an area of 0. That's what's going on there. Okay, on question 12, we're going to let u equal 6z plus 1, du is equal to 6 dz. So we need to change a few things up. This is going to be 1. Let's write this up here. This is going to be 1/6 times the integral from 2 to 5 of 6. Now I'm going to rewrite this. Instead of a square root, I'm going to give it a power of 1/2, and then I'm going to move it up to the numerator and give it a power of negative 1/2. So this is going to be parenthesis 6z plus 1 to the negative 1/2 dz. Now we can make these substitutions. This is going to be 1/6 times the integral of u to negative 1/2 du. Now we find the antiderivative. There's going to be 1/6 times u to the positive 1/2, and then instead of dividing by 1/2, we're going to times it by 2. And that's going to be evaluated from 2 to 5, but we need to undo the substitution here. So this is going to be 1/6, and then 6z plus 1 to the 1/2 power. That's going to be evaluated from 2 to 5. So this becomes 1/6 times, actually I forgot a 2 right there. It's 2 times u to the 1/2, so that should be 2. Let me rewrite this. 2 times 6z plus 1 to the 1/2. Now, plug a 5 in for this z. 6 times 5 is 30 plus 1 is 31, so this is 2 times the square root of 31. Now we evaluated 2, so 2 times 6 is 12 plus 1 is 13, so this is 2 times the square root of 13. Now if we multiply 1/6, distribute the 1/6, we're going to get square root of 31 over 3 minus square root of 13 over 3. Okay. To find the area between two curves, we need to find a definite integral, but we have to have the bounds of integration. Sometimes the bounds are given, sometimes we have to find where the two graphs intersect each other to form that bounded region. So since the bounds of integration are not given, we've got to set the two functions equal to each other. So x squared plus 6x plus 9 equals 5x plus 15. This is a quadratic equation that hopefully we'll be able to solve by factoring. So we get one side equal to 0. So it's going to be x squared plus x minus 6 equals 0, which factors into x plus 3 times x minus 2 equals 0. And so the solution of x equals negative 3 and x equals 2. These are the two x values where these functions would cross. That represents our bounds of integration. So now we also need to figure out between these two bounds of integration which function is the higher function. A couple things you could do if you think about the type of functions that are occurring here. This is a quadratic function, meaning it's going to be a parabola. This is a linear function. Okay. A couple things you could do. You could find graphically what's going on here. The function 5 times x plus 3 is 5x plus 15. So go to 15, and then the slope is positive 5. So instead of going up 5 and over 1, we can go down 5 and to the left 1. Okay, and then f of x equals x squared plus 6x plus 9. That's a parabola. Now, if we consider this in a different form, x squared plus 6x plus 9, it's the same as x plus 3 times x plus 3, or rather, x plus 3 squared. Now, this is vertex form. The x plus 3 inside the parenthesis moves the graph 3 units to the left. There are no transformations to move the graph up, so this is a parabola that slides along the x-axis 3 units. So there's the vertex, and the parabola is facing up like this, and it would eventually cross through the straight line. So we have one here where the graph crosses through, and here where the graph crosses through. I mean, this is just a rough sketch. We have this area of the graph right there. So thinking about it graphically, between the two bounds of integration, negative 3 and positive 2, this is the g function. Okay, this is the f function. So between the two bounds of integration, the g function is above the f function. Okay. Other thing you can do, if you don't want to spend the time graphing, is between the two bounds of integration, negative 3 and 2, you can test values in each function to see which one produces the highest value. 0 is between negative 3 and 2. So if you find f of 0, then those two disappear. F of 0 then is equal to 9. If you try to find g of 0, then 0 plus 3 is 3. 5 times 3 is 15. So g of 0 is equal to 15. So between the two bounds of integration, you test a point of 0, and that proves that the g function has the higher value, so it's above. That's important because to find the region, the area of the region between two functions, you take the integral between the two bounds of integration. That's going to be negative 3 and 2, and then you have to take the difference of the two functions, but it needs to be done in the right order. Since the g function is higher, it's g of x minus f of x dx. Okay. So that's going to change the integral from negative 3 to 2 of 5x minus 15 minus x squared minus 6x minus 9 dx. Remember, we're subtracting the entire f function, so change the sign of every term. This turns into the integral of negative 3 to 2 of negative x squared minus x. See, that's a plus 15. Sorry, it's 5x plus 15. 15 minus 9 is 6. This turns into the integral from negative 3 to 2 of negative x. Well, we take the integral, let's just take the integral separately here. This is going to be the integral of negative x squared, that's negative x to the third over 3. The integral of the middle term there is negative x squared over 2, and then plus 6x and that's going to be evaluated from -3 to 2. Now that turns into -8 thirds minus 2 plus 12. This is the antiderivative. This is the antiderivative here, and this is its value evaluated at 2. Now we subtract the antiderivative evaluated at -3. So that's going to turn into 9 minus 9/2 minus 18. This inside of here, if you've simplified everything, turns into 22 thirds. Now we're subtracting a -27 halves, which means we're adding. Simplifying that fraction is 125/6. Technically, since it's an area, it's 125 over 6 units squared. Okay, consumer and producer surpluses. We've been given a demand function here and a supply function here. Consumer and producer surpluses is a lot like the problem we just did. It's finding the area bounded between two curves. We have to have the bounds of integration. Just a rough sketch of what's happening here. We have the demand function here, the supply function. So they intersect here. This is the equilibrium point. So this is going to give us an x value, which is units produced. It also gives us a price. Okay. The area under here is a producer surplus, so it's it's the difference between the price function and the supply function. The area here is the consumer surplus. It's the integral, it's the area beneath the demand function and the price. So what we first need to do is find this equilibrium point to give us to give us the bound of integration and also the price, so we can figure out our definite integrals. So to find the equilibrium point, we have to set supply equal to demand. So 36 minus 0.35x equals 0.05x. Adding negative 0.35 or adding 0.35x to both sides gives 36 equals 0.40x, or just 0.4. 0.4 is the same as 2/5. So this is 2/5 x. Now multiply both sides by 5/2. And then half of 36 is 18. 18 times 5 is 90, so x is equal to 90. Now if you plug 90 into either the supply function or the demand function, it turns out the price is 9/2. So we need to do two definite integrals. Let's do let's do producer surplus first. That is probably going to be the easiest. Producer surplus, that's the integral from 0 to 90. So we have our bound now. The two graphs intersect here at 90, and they're also bounded by the y-axis. That's when x is equal to 0. From 0 to 90, now this right here, this is the producer surplus. Okay, the top curve is price, which is 9/2. Now we subtract the bottom curve, which is the supply demand, 0.05x dx. Now 0.05 is the same as 1/20th. So when we integrate and find the antiderivative, this is going to be 9/2 x minus 1/40th x squared, and that needs to be evaluated between 0 and 90. So this is 9/2 of 90 minus 1/40th of 90 squared, and then we would have to subtract the antiderivative evaluated at 0, but the antiderivative here evaluated at 0 is just 0, so we don't have another piece to that. So to figure out 9/2 times 40 minus 1/40th times 90 squared. So that 9/2 of 90 is 405, and then 1/40th times 90 squared. 90 squared is 8100. 1/40th of that is 405 halves. So if we start with 405 and we take away 405 halves, then we're left with 405 halves. That's in terms of dollars. So the producer surplus is $405. Now the consumer surplus is the interval from 0 to 90. Now the top function is the demand function, which is 36 minus 0.35x. Now we minus the bottom function, which is the price function, 9 halves. Now the antiderivative, that, well, I guess we can simplify 36 minus 9 halves is 63 halves. 36 minus 9 halves is 63 halves. When you take the integral of 63 halves, you get 63 halves times x. And then 0.35 as a decimal is 7/20ths. So then the integral of 7/20ths x is 7/40ths x squared, and that's going to be evaluated between 0 and 90. So this antiderivative evaluated at 90 is 63 halves times 90 minus 7/40ths times 90 squared, which is 8100. And then we would minus the antiderivative evaluated at 0, but that's just going to be 0. So 63 halves times 90 is the same as 63 times 45. And that's equal to 2,835. Now, 7/40ths of 8100 is 2835 halves. So if you subtract 2835 minus 2835 halves, the answer is 2835 halves. And that's in terms of dollars.